And welcome back. So this is our second short video on superposition, and this time we are doing an example with two pumping wells, so two transient solution with pumping. So here's the setup. So we calculate the drawdown at an observation well due to the pumping in two different wells. The aquifer has a given transmissivity of 300 square meters per day, storativity of 6×10⁻⁴. Well number 1, which is located at 30 meters from the observation well, produces water at a rate of 550 cubic meters per day, while well number 2, which is at 40 meters from the observation well, has a discharge of 1100 cubic meters per day. The observation well drawdown at a time of 200 days is required. Okay, so we want to know what will be the drawdown 200 days after we start pumping those two wells in the observation wells. So again, you can think of this as a dewatering problem almost, like what if we wanted to dewater at the observation well, right? What if that's a construction site and we want to drop the water table there so we can work? Okay, what would happen in 200 days? Would that be enough or not? Okay, so this is the setup. We have the observation well, the two wells, the two pumping wells, and we want to know after 200 days what happens. Now, we know what the drawdown in one well is, right? Because that's our Wells function for a confined aquifer. So, whoops. Here, right, so Q over 4 pi T, W of U, right, the Wells function. So we already know this, if, assuming this is a confined aquifer. Now on the right-hand side here, again, superposition, we have two wells, so the drawdown from the two wells is the sum of the drawdown from each individual well, so we can write this twice and we're done. Now, U, we already know what it is, right, from our previous lectures, so U equals R squared S divided by 4t. So again, remember that u is time essentially, or 1 over time, right? So 1 over u, the x-axis of the well function, is time. So u is, again, 1 over time right here. This is 1 over time, right? So this is really important too. So it's a modified time modified by some known quantities. So again, here, you can see that we know all those constants, right? So R is the distance to the observation well. We know that for each well. The storativity and the transmissivity, of course, are the same. It's the same aquifer, and that's it. And then time, this is what we require. So we want the drawdown after 200 days. So we know time as well. So we can calculate U1 and U2, no problem. Okay, so we plug in and we find that U1 is 2.2e minus 6, U2 is 4e minus 6. Now, at 200 days, this is pretty much, we can use the Jacob approximation or the long time approximation of the Wells function. Of course, you could also just, use the Wells function and find the tabulated value of it, or you could use some numerical, method to calculate W of U, knowing U. But here I'm just reminding you of the Jacob method, basically, that at large times or small u's, you can approximate the Wells function by the natural log of 0.56 divided by U. And since we know U, we can evaluate WU, using this simple approximation. Now, if we do this, we find WU1, WU2. And finally, we can plug that into our original, sum, right? The drawdown is the sum of the two wells. So again, Q over 4 pi, this is the transmissivity for the first well, and then WU1 now. And then Q over 4 pi T for the second well, WU2 right here. And then if we sum those two, we get the drawdown equals 5.27 meters. So after 200 days, right, after 200 days, the drawdown in the observation well will be 5.27 meters due to the pumping of those two wells. Okay, I hope that was a good review, a simple example of how to use, again, the Wells function in a confined aquifer in this case. In future examples, we'll also do examples in unconfined aquifers. So the next lecture, the next video will be on boundaries. So the next couple of videos will be on boundaries basically, and how we can use this principle of superposition to account for boundaries and those imaginary wells, basically imaginary solutions. So this is the next lectures. Thank you.